In the spring of 1942, as Luftwaffe fighters dominated European skies, British engineers at Rolls-Royce stared at intelligence reports showing America's new P-51 Mustang failing catastrophically above 15,000 feet. The aircraft possessed brilliant aerodynamics, but carried an engine that choked at altitude. What happened next would transform aerial warfare forever. A desperate transatlantic partnership that turned Britain's most guarded secret into America's deadliest weapon. Derby, England, 14th March 1942, 06:47 hours. The Rolls-Royce factory floor vibrated with the thunder of Merlin engines being tested in reinforced concrete bays, their 12-cylinder roar audible 3 miles away despite blackout regulations. Outside, fog mixed with coal smoke from emergency generators, the temperature hovering at 4 degrees Celsius. Shrapnel scars pockmarked the factory's brick facade from Luftwaffe raids 6 months prior, hastily patched with mismatched mortar. Inside, production continued without pause. Stanley Hooker, 47 years old, chief engineer of the Supercharger Division, stood before a blackboard covered in thermodynamic calculations, chalk dust coating his worn tweed jacket. His hands trembled not from cold, but from exhaustion after 16-hour shifts, sustained on rationed tea and determination. Before him sat Air Ministry officials whose expressions revealed strategic panic, poorly disguised by bureaucratic stoicism. The numbers told an unforgiving story. Bomber Command was losing aircraft at rates that would render operations unsustainable within 8 months. Fighter escorts could not reach targets deep in occupied Europe. Luftwaffe interceptors operated with impunity above 20,000 feet, systematically destroying Allied bomber formations. "Gentlemen, we are losing this air war," stated Group Captain Richardson, spreading reconnaissance photographs across the conference table. Each image documented burning bombers, broken formations, empty airfields. "Last week we lost 43 Lancasters in 3 raids, 43, each carrying 7 men. That is 301 trained aircrew gone because we cannot protect them at operational altitude." The strategic mathematics were brutal and undeniable. German fighters equipped with fuel injection and supercharged engines dominated the vertical battlefield. British Spitfires, though magnificent, lacked range for escort duties. American P-38 Lightnings suffered mechanical failures in European weather. The new P-47 Thunderbolt was effective but consumed fuel voraciously, limiting penetration depth. Then came the P-51 Mustang, developed by North American Aviation for the RAF, possessing aerodynamic efficiency unprecedented in fighter design. Wind tunnel testing showed drag coefficients that made engineers question their instruments. The airframe promised range exceeding 1,000 miles with external tanks, but the Allison V1710 engine, installed by Americans, failed catastrophically above 15,000 feet, rendering the aircraft tactically worthless for European combat, where engagements occurred between 20,000 and 30,000 feet. Ronald Harker, RAF test pilot temporarily seconded to Rolls-Royce, had flown the Mustang at RAF Duxford 3 weeks prior. His report was diplomatically worded, but technically devastating. Exceptional handling characteristics and range. Performance above 15,000 feet entirely inadequate for combat operations. Allison engine loses 40% power above operational ceiling. Aircraft cannot engage FW-190 or BF-109 under combat conditions. The proposal emerged from this confluence of desperation and opportunity. Hooker's team had developed the 2-stage, 2-speed supercharged Merlin 61, transforming high-altitude performance dramatically. Spitfire Mark 9s equipped with this engine could reach 42,000 feet and maintain combat power throughout the altitude range. Intelligence indicated the modification reversed tactical balance against Luftwaffe fighters. The question was whether this engine, Britain's most strategically valuable technology, developed through years of metallurgical research and thermodynamic innovation, could be installed in an American airframe and produced in quantities sufficient to matter. The institutional resistance was immediate and predictable. Air Ministry officials argued that sharing Britain's most advanced aero engine with Americans risked technological secrets reaching enemy hands if facilities were bombed or security compromised. Rolls-Royce production was already stretched beyond peacetime capacity, workers operating under conditions that violated every pre-war safety regulation. Factories functioned through bombing raids, production continuing even as German ordnance detonated hundreds of yards away. The company had no spare manufacturing capacity for experimental modifications of foreign aircraft. But Group Captain Richardson possessed strategic clarity, born from watching too many young men burn. The Americans have the airframe, we have the engine. Separately, both are inadequate. Combined, they might provide the range and altitude performance to escort bombers to Berlin and back. Gentlemen, we are not discussing commercial competition. We are discussing whether this island survives as a free nation or becomes a German province. If we do not solve the escort problem, bomber command becomes unsustainable, invasion becomes inevitable, and this conversation becomes irrelevant because we will be conducting it in a prisoner camp. The silence that followed carried weight of mortality statistics and strategic desperation. Hooker studied his calculations, considering engineering challenges that seemed insurmountable. The Merlin weighed 1,640 pounds. The Allison weighed 1,195 pounds. The weight difference would affect the Mustang's center of gravity, potentially rendering the aircraft unstable. Engine mounting points were entirely different. Cooling systems required complete redesign. Propeller specifications needed recalculation. Fuel systems must be modified. The work represented 6 months of development under laboratory conditions with unlimited resources and no time pressure. They had 6 weeks, limited materials, and Luftwaffe bombing the facilities every third night. But Hooker remembered something fundamental about British engineering culture that Germans consistently underestimated. When told something was impossible, the natural response was to prove otherwise through sheer, bloody-minded determination, improvisation, and willingness to work until the problem was solved or the person collapsed. "We will make it work," Hooker stated quietly, the declaration carrying more weight than any theatrical speech. "We have no alternative." The project began that afternoon with a single Mustang airframe shipped from America, a Merlin 61 pulled from Spitfire production despite protests from Fighter Command, and a team of engineers who understood that failure meant watching friends die in burning aircraft because the solution was technically possible but bureaucratically inconvenient. Hucknall Airfield, Nottinghamshire, April 1942. The facility operated under conditions that made pre-war engineers question sanity. The experimental hangar, originally designed for prototype testing under controlled conditions, now functioned as combined workshop, design office, and production facility. Lighting was unreliable due to generator fuel rationing. Heating was non-existent except for portable paraffin heaters positioned near workbenches to prevent tools becoming too cold for comfortable handling. Outside, rain fell with the persistent grey monotony characteristic of English spring, turning the airfield into expansive mud that swallowed equipment and tested patience. The Mustang sat in the center of the hangar under harsh work lights powered by emergency generators, its Allison engine removed, exposing the skeletal structure of engine bay and mounting framework. The Merlin 61 sat on a wheeled cradle nearby, its polished aluminium casings reflecting light, 12 exhaust stubs pointing skyward like cathedral organ pipes. Between these two machines stood the engineering team that would marry them. 12 men, ranging from 56-year-old veterans of Great War aircraft development to 23-year-old draftsmen fresh from technical colleges, working 16-hour shifts sustained on rationed tea, irregular meals, and conviction that their work mattered existentially. The technical challenges emerged immediately with brutal clarity. the Merlin mounted through 4 primary points in Spitfire airframes. The Mustang's engine bay was designed for completely different geometry. Creating new mounting brackets required precision machining using equipment designed for pre-war production tolerances, now worn from continuous wartime operation. The machine shop operated with reduced staff because skilled workers were conscripted into military service, leaving positions filled by retired craftsmen recalled from pension and women recruited from civilian life, learning precision metalwork under pressure that permitted no errors. Weight distribution represented critical engineering challenge that could determine whether the modified aircraft flew properly or killed the test pilot during first takeoff. The Merlin's additional 245 pounds concentrated forward of the center of gravity, affected longitudinal stability in ways requiring complex aerodynamic calculations. The team performed computations using slide rules and logarithm tables, checking results 3 times because mathematical errors would manifest as uncontrollable flight characteristics. Wind loading calculations filled notebooks, each page covered in equations exploring stability margins under various flight regimes. Cooling presented another layer of complexity that consumed weeks. The Merlin generated significantly more heat than the Allison at combat power settings. Coolant radiators designed for American engine specifications were inadequate for British power plant requirements. The solution required repositioning the radiator installation beneath the fuselage, redesigning ducting to maximize cooling efficiency whilst minimizing aerodynamic drag. Engineers fabricated prototype ducts from sheet aluminium using techniques borrowed from automotive workshops, testing airflow patterns using smoke generators and empirical observation because proper wind tunnel testing was impossible given time constraints and facility unavailability. Propeller selection represented another engineering puzzle with strategic implications. The Merlin's power characteristics and rotational speed differed substantially from the Allison. Propeller blade pitch, diameter, and rotational direction required recalculation. The solution involved adapting propellers from Spitfire production, modifying blade pitch mechanisms, and accepting that initial flight testing would reveal handling characteristics impossible to predict through calculation alone. The work proceeded against constant environmental hostility that tested physical and psychological endurance. Air raid sirens wailed 3 to 4 nights weekly, forcing evacuation to concrete shelters, whilst Luftwaffe bombers targeted industrial facilities across the Midlands. The team learned to recognize aircraft engine sounds, distinguishing British bombers returning from operations from German intruders hunting targets of opportunity. Production continued even during raids, when regulations theoretically prohibited it. Engineers working by torchlight when generators shut down, trusting that fate or luck would spare them from direct hits. Material shortages created daily crises requiring creative improvisation, characteristic of British wartime culture. High-grade aluminium required for structural components was allocated strictly by Air Ministry priority lists. When requisitions were delayed, engineers cannibalized damaged Spitfire airframes, awaiting salvage, cutting brackets from wrecked fighters to build the modification that might save future pilots. Fasteners specified in design documents were unavailable. Substitutes were identified from obsolete aircraft parts bins, modified to fit, and installed with crossed fingers and engineering judgment accumulated through decades of practical experience. The human cost accumulated invisibly but inexorably. Hooker's weight dropped from 12 stone to 10 stone 6 pounds within 3 months. Sleep deprivation became normalized. Men worked until collapse was imminent, slept 4 hours, returned to resume work. Marriages strained under absence and exhaustion. Letters from wives described rationing hardships, children growing up with fathers perpetually absent, elderly parents struggling without support. One engineer received notification that his home in Coventry was destroyed by bombing. He took 2 hours to arrange temporary housing for his family, then returned to continue work, because stopping meant more homes would burn. The culture sustained itself through characteristically British coping mechanisms that outsiders found incomprehensible. Humour remained dry and persistent despite circumstances. When structural calculations revealed weight distribution problems requiring extensive redesign, the team's senior structural engineer commented, "Well, at least Jerry hasn't bombed the mathematics yet, though given our progress, perhaps he should." Tea breaks became ritualized moments of normality where conversation deliberately avoided work topics, discussing cricket scores, betting pools on when rationing might end, and elaborate complaints about the quality of powdered eggs. By late June, the modification reached critical testing phase. The Merlin was installed, cooling systems tested, fuel lines pressure checked. The aircraft sat ready for engine runs, looking simultaneously familiar and alien. Mustang airframe married to British power plant, product of transatlantic partnership born from strategic desperation. Ground testing began cautiously, engineers monitoring temperatures, pressures, vibrations, searching for problems that would manifest as catastrophic failures during flight testing. The initial engine run occurred at dawn on 1 October 1942, witnessed by engineering team, Air Ministry observers, and Rolls-Royce executives who understood that corporate reputation and national survival were equally invested in the outcome. Hawker sat in the cockpit, methodically working through startup procedures, whilst ground crew manned fire extinguishers positioned at strategic locations. The Merlin caught with characteristic authoritative roar, 12 cylinders firing in sequence, exhaust note different from American engines, but unmistakably powerful. Hawker advanced throttle gradually, watching instrument readings, feeling vibrations through controls, assessing whether the modification would kill him or validate months of exhausting work. Engine parameters remained within acceptable limits. Vibration was present but not excessive. Temperatures climbed steadily but stabilized within operational range. After 20 minutes of ground running at various power settings, Hawker shut down and emerged from the cockpit, wearing expression of cautious optimism that British Reserve translated into highest praise. "She runs properly," he stated simply. "We will fly her tomorrow." Rechlin Luftwaffe Test Center, Germany, March 1943. Oberst Heinrich Baer reviewed intelligence reports with growing unease that contradicted every tactical assumption underlying Luftwaffe operational doctrine. American bomber formations that should have been massacred over Schweinfurt returned with acceptable loss rates. Escort fighters that previously turned back at German borders now penetrated to target areas, engaging Luftwaffe interceptors with effectiveness that seemed impossible given previous performance assessments. The reports were initially dismissed as exaggeration from Jagdgeschwader commanders seeking excuses for unacceptable loss rates. But patterns emerged with undeniable consistency. Combat film from gun cameras showed American fighters at 28,000 feet maintaining formation and engaging aggressively rather than struggling for altitude as previous encounters demonstrated. Speed measurements indicated velocities exceeding expectations by 40 miles per hour at combat altitudes. Kill ratios shifted dramatically. Previous engagements showed German fighters destroying American escorts at 3-to-1 ratios. Current statistics indicated parity or worse. German intelligence analysts recognized the aircraft type, P-51 Mustangs, supplied to RAF under Lend-Lease. Previous assessment classified them as low-altitude tactical fighters, unsuitable for high-altitude combat operations due to Allison engine limitations. That assessment was demonstrably obsolete. Something fundamental had changed. Initial theories suggested Americans developed new engine variant with improved altitude performance. Technical intelligence disagreed. Wreckage analysis of downed Mustangs revealed British Merlin engines installed where American Allisons were expected. The discovery created doctrinal confusion at Luftwaffe headquarters. British engines in American airframes represented collaboration that German strategic thinking considered improbable. The German military culture emphasized national pride and technological sovereignty. Sharing advanced engine technology with foreign powers contradicted institutional assumptions about how nations behaved. Intelligence analysts debated whether installation was emergency field modification for limited aircraft or represented systematic production program. The answer arrived through reconnaissance photographs of American factories showing assembly lines, producing Merlin-engined Mustangs in quantities that suggested industrial-scale manufacturing. The strategic implications crystallized with disturbing clarity. The modified Mustang possessed range to escort bombers to Berlin and return, altitude performance matching Luftwaffe interceptors, and aerodynamic efficiency providing fuel endurance exceeding German fighter capabilities. The combination eliminated the operational sanctuary that Luftwaffe fighters exploited, attacking bomber formations beyond escort range. That sanctuary was collapsing as American production delivered Merlin-equipped Mustangs in quantities indicating thousands rather than hundreds would enter service. Baer recognized the pattern from earlier war phases. German tactical aviation achieved dominance through technological superiority and doctrinal innovation. Bf-109Es defeated French and British fighters through fuel injection, enabling negative G maneuvers and superior altitude performance. FW-190s, introduced in 1941, outperformed Spitfire Mark Vs comprehensively, regaining air superiority when Britain threatened parity. Each German advantage was temporary until opponents developed countermeasures. The Merlin Mustang represented countermeasure that neutralized German advantages completely, whilst introducing new disadvantages. The American fighter possessed greater range, similar performance, and would be produced in quantities German industry could not match. Luftwaffe responses followed predictable patterns rooted in institutional culture, emphasizing aggressive tactics and pilot skill. Jagdgeschwader commanders received directives instructing modified engagement doctrines. Avoid prolonged combat with Mustang escorts. Engage bombers directly using superior climb rate to attack from above. Disengage rapidly before escorts could respond. The tactics represented doctrinal improvisation, attempting to preserve operational effectiveness against opponents whose capabilities now matched or exceeded German fighters. The first major engagement demonstrating new strategic reality occurred over Brunswick on 11th January 1944. The 354th Fighter Group flying P-51Bs encountered Jagdgeschwader 11, intercepting B-17 formations. German pilots executed standard tactics, climbing above bomber altitude, positioning for diving attacks through formations. But Mustang escorts matched the climb, maintained position during German attack runs, and engaged during disengagement phase when German fighters traditionally escaped through superior speed. The engagement resulted in 16 German fighters destroyed for 4 American losses. Similar ratios repeated across subsequent operations. German pilot accounts revealed psychological shift beyond tactical statistics. Previous combat against American escorts involved limited engagements before fuel constraints forced American withdrawal. Luftwaffe pilots controlled timing and engagement intensity. Mustang escorts eliminated that control. They remained throughout missions, engaged persistently, and possessed performance margins preventing easy disengagement. The psychological advantage shifted. German pilots entered combat, knowing American escorts could pursue them throughout operational airspace, transforming what was previously controlled tactical environment into sustained attrition battle, favoring side with numerical superiority. General Lieutenant Adolf Galland, inspector of fighters, understood strategic mathematics with clarity born from flying 705 combat missions. "The Americans have done something remarkable," he observed during staff conference at Luftwaffe High Command. They built an escort fighter combining range, performance, and reliability. Worse, they are producing them in quantities we cannot match. Our pilots are excellent, our tactics are proven, but we are fighting an opponent who can engage us at any altitude, pursue us throughout operational radius, and replace losses faster than we destroy them. Gentlemen, we are losing the mathematics of attrition. The doctrinal incompatibility was fundamental. German fighter doctrine emphasized individual pilot skill, aggressive tactics, and technological superiority, enabling small numbers of excellent pilots to achieve disproportionate results. The doctrine worked brilliantly when German fighters possessed performance advantages and controlled engagement terms. Mustang escorts eliminated both conditions. Performance was now equivalent, and numerical superiority combined with superior range meant American forces controlled engagement timing and intensity. German fighter arm found itself fighting attrition battle using doctrine designed for qualitative superiority, confronting opponent who possessed quantitative superiority supported by industrial capacity producing replacement aircraft and pilots faster than combat consumed them. By spring 1944, intelligence estimates indicated American forces would deploy over 1,000 Mustangs to European theater by summer. German fighter production struggled to maintain 500 operational aircraft after replacing combat losses and mechanical attrition. The strategic balance was inverting. Luftwaffe, that dominated European skies in 1940, faced aerial attrition that would render defense operations unsustainable within 6 months. The transformation was rooted in Anglo-American partnership that German strategic thinking failed to anticipate. British engineering excellence combined with American industrial capacity created weapon system neither nation could produce independently. The Merlin engine represented decades of metallurgical research and thermodynamic optimization. The Mustang airframe reflected American aerodynamic sophistication and manufacturing efficiency. Combined, they produced fighter that excelled in every performance regime whilst being produced at industrial scale, unprecedented in aviation history. German tactical responses proved inadequate against systematic transformation. Luftwaffe introduced jet fighters, providing performance superiority, but production numbers were insufficient to affect strategic balance. Training programs emphasized tactics optimized against Mustang characteristics, but tactical excellence could not overcome numerical disadvantage. Industrial priorities shifted to fighter production, but German manufacturing capacity could not match American output even operating at theoretical maximum efficiency. The perplexity was genuine and profound. How did opponents who struggled with altitude performance 6 months prior suddenly deploy fighters dominating operational environment? How did industrial partnership between nations produce results exceeding what either achieved independently? The answers revealed strategic blindness at heart of German military culture, underestimating opponent adaptability, dismissing industrial capacity as strategically decisive factor, and failing to recognize that technological secrets shared with allies represented force multiplication rather than security compromise. Derby, England, 9th of May 1945, Victory in Europe Day. The Rolls-Royce factory floor stood silent for the first time in 6 years, machinery powered down, the perpetual thunder of engine testing replaced by almost unsettling quiet. Workers gathered outside, despite grey drizzle characteristic of British spring, listening to Churchill's broadcast announcement confirming German unconditional surrender. The relief was profound, but tempered by exhaustion, accumulated through years of relentless production, under conditions that violated every peacetime standard. Stanley Hooker stood among his team, watching workers embrace and cry openly, emotional release after years of disciplined effort. The statistics were staggering in their magnitude. 55,000 Merlin engines produced between 1942 and 1945, specifically for Mustang installation, manufactured in British and American factories through technology transfer unprecedented in industrial history. The Packard Motor Company in Detroit received complete Merlin specifications, tooling designs, metallurgical processes, and engineering support, enabling American production of British engine at scale impossible for Rolls-Royce alone. Combined Anglo-American production delivered engines transforming strategic balance in European and Pacific theaters. The operational impact was quantifiable through statistics that represented thousands of individual human stories. P-51 Mustangs flew 213,873 sorties in European theatre, destroying 4,150 enemy aircraft whilst losing 2,120 to all causes. The kill ratio was remarkable. The strategic impact was transformative. Bomber command loss rates decreased from 6.8% per mission in early 1943 to 1.9% by 1945. The reduction represented 12,000 aircrews who survived because escort fighters possessed range and performance-protecting bomber formations throughout operational missions. German fighter arms sustained losses exceeding replacement capacity by spring 1944, rendering aerial defense progressively unsustainable until collapse became inevitable. The partnership model represented innovation beyond engineering achievements. British expertise in high-performance aero-engine development combined with American industrial mass production capability created result exceeding what either nation achieved independently. The technology transfer was comprehensive. Rolls-Royce provided complete specifications, including proprietary metallurgical processes for supercharger impellers, thermodynamic calculations for cooling systems, and quality control procedures developed through decades. American manufacturers contributed industrial engineering, optimizing production for mass manufacture, developing tooling reducing machining time, and implementing quality assurance protocols, enabling factory workers with limited training to produce engines meeting strict tolerances. The cultural dimension mattered equally. British engineering culture emphasized craftsmanship, incremental optimization, and maintaining standards regardless of pressure. American industrial culture emphasized scalability, process efficiency, and pragmatic problem-solving. Combined approach produced engines maintaining Rolls-Royce performance standards whilst being manufactured at rates American automotive industry considered routine, but British aviation industry thought impossible. Packard factories in Detroit produced 55,000 Merlin engines between 1942 and 1945, using assembly line techniques adapted from automobile production, achieving output exceeding total Rolls-Royce production across entire war. The individuals whose determination enabled this transformation received varying recognition, reflecting British cultural attitudes toward publicity. Hooker continued post-war career at Rolls-Royce, eventually becoming company chairman, his contributions recognized through professional success rather than public acclaim. Ronald Harker received modest decorations but remained largely unknown outside aviation circles. The factory workers who operated lathes through bombing raids, the draftsmen who refined designs under impossible deadlines, the test pilots who validated modifications risking their lives, most returned to civilian obscurity, their contributions acknowledged primarily through personal satisfaction that their work mattered. The strategic lessons transcended immediate military applications. The program demonstrated that technological secrets shared with trusted allies represented force multiplication rather than security compromise. German reluctance to share advanced technology with Axis partners limited collaborative potential. Allied willingness to transfer technology created combined capabilities exceeding individual national efforts. The industrial integration pioneered during Merlin Mustang program established precedents for post-war NATO standardization and collaborative defense programs. The post-war analysis by military historians recognized transformative significance. The Merlin-Mustang partnership represented an inflection point where Allied industrial cooperation achieved strategic decisiveness, concluded official RAF history. British technological excellence, combined with American manufacturing capacity, created weapon system that shifted aerial balance irreversibly. The program demonstrated that modern warfare was increasingly determined by industrial capacity, technological innovation, and Allied cooperation rather than individual battlefield excellence. The political dimension mattered deeply to Anglo-American relations. The partnership occurred during a period when British global influence was declining whilst American power was ascending. The technology transfer could be interpreted as acknowledgement of changing power dynamics, Britain contributing expertise to American platform. But participants understood different narrative. Two nations, recognizing complementary strengths and cooperating without concern for prestige or competitive advantage. Churchill observed in 1945, "The Merlin engine in American fighters represents finest tradition of Allied cooperation. We provided our best engineering. Americans provided industrial might. Together, we achieved what neither could accomplish alone." The engine production continued post-war for civilian applications, Merlins powering airliners and racing aircraft, the distinctive sound becoming cultural icon, representing both wartime achievement and post-war optimism. The technology influenced subsequent engine development. Lessons learned during supercharger optimization, metallurgical advancement, and quality control standardization informed jet engine development that defined post-war aviation. The human stories remained most compelling. Engineers who worked 16-hour shifts, preventing social collapse, received no parades. Their reward was survival and knowledge their contribution mattered. Factory workers who operated machinery during bombing raids returned to peacetime employment, rarely discussing wartime experiences. Test pilots who validated modifications, risking death with each flight, transitioned to civilian aviation or military retirement. Their legacy existed in veterans who survived bomber missions because escorts reached them, in families not receiving death notifications because fighters protected husbands and sons, in civilization preserved because industrial democracies mobilized their combined capabilities toward collective survival. On that drizzly May afternoon in Derby, as Churchill's voice faded and workers began contemplating return to peacetime normality, the Rolls-Royce team understood something profound about capability emerging from crisis. When circumstances demanded impossible achievement, when survival required transcending individual limitations, when national existence depended on collaboration without regard to pride or competitive advantage, ordinary people accomplished extraordinary outcomes. The Merlin Mustang program proved that technological excellence, industrial capacity, and human determination, combined through Allied partnership, could transform strategic reality and ensure that free nations remained free. The silence in the factory was temporary. Production would resume for civilian purposes, the machinery would thunder again, and life would continue. But for that moment, standing in the rain, workers who built 55,000 engines in 4 years allowed themselves recognition that their impossible achievement helped save Western civilization. That recognition was characteristically understated, acknowledged through quiet nods and modest smiles, but profound nonetheless. The Merlin Mustang story reveals how British ingenuity, combined with Allied determination, changed history. If you're fascinated by the untold stories of innovation and resilience that shaped the war, subscribe to our channel for more deep dives into extraordinary engineering triumphs. Share your thoughts in the comments. What other wartime partnerships deserve recognition? Hit that notification bell so you never miss another remarkable tale from history's most decisive conflict. Cheers.